basically what we said, and I want to add a few more things. Kind of, it's good as a review, and at the same time, so we talked about chapter 10 having alcohols, thiols, and amines, and I said that normally when you think of chemical reactions, you look at the bonds. So alcohols have polar bonds. You all know that these two bonds are polar. So this is polar, and this is also polar. So normally the polar bond is easier to break than a non-polar bond. But you all know that alcohols are stable. Put them in anything, they're used as solvents. So if they're used as solvent, it means that they're not going to react easily. The question is why? Even though the bonds are polar, so normally if the bonds are polar, it should be easy to break. Yes, the bonds are short, they're not long. That's true. But you will see later that short bonds can also be broken if they're polar, but not in their alcohol. So this is what I forgot to say, is that alcohols make hydrogen bonds. Okay? So because they make hydrogen bonds with each other, you know that they make hydrogen bonds. So these bonds are protected. So that's the reason they're even less reactive, because they make hydrogen bond between them. And this hydrogen bond keeps them tied to each other, so hard to weaken. Is that clear? So everybody understands now that alcohols are not reactive. A big part of it is because they make hydrogen bonds. So their OH is attached to each other, and it's hard to really break them. So what are the reactions we saw last time? We saw substitution, and all the substitution we needed strong acids. So we put the list of acid, HCl, HCl, HBr, and HI. You all know that as we go down here, the bond gets longer. So this is the strongest acid, and this is the weakest acid. So because this is the strongest, this is the one that's going to react the fastest and the best. Okay? So alcohols will react with HI, they will react with HBr, they will not react with HF. We already said that because HF is weak. It's not a strong acid. And for HCl, the reaction is very slow. Okay? So it reacts here, but it doesn't react very well with HCl because it's not as strong as HI and HBr. So please make sure you write it down. The reason this is very slow, for what reason? It's only because it's not very strong, not very reactive. Okay? Now, why am I saying this? Because you will see it later when we start using different reactants for the same compounds. You have to start thinking this way constantly. So I'm kind of setting the tone, trying to help you out remember why is it that one reacts and one doesn't. And again, it has to do with the strength of these acids. The other thing we said is the alcohol can be primary, secondary, or tertiary. Okay? So if you look at the alcohols, so they are primary, secondary, and tertiary. If you take the primary alcohol and you add HBr, for example, you're going to end up with RBr plus H2O. That's what we did last time. We did this. So I don't need to go back again to the mechanism. So what is the steps? How many steps was that? Two. What is the first step? Protonation. And why is the protonation necessary? Is when it protonates here, it makes the bond weak. And then it makes a good leaving group. Water is a better leaving group than OH minus. Is that clear? So what is leaving is water. Water is a much better leaving group than OH minus. So the first step is protonation, and what's the second step? It's it's elimination, but at the same time, it happens in one step. It's a substitution. Agree? The water leaves and the halogen attach. What is the mechanism there? Is it 2 steps or 1 step? One. So what is that called when it's a 1-step substitution? SN2. So these are the things you should remember. So step 1 is protonation. And step 2 is an SN2. 1 step. So the water leaves and the halogen attacks. Now let's do the tertiary. What did we say about the tertiary? Also reacts. And here I'm using HBr because we already established that these two are the strongest. They work pretty well. Okay? And then you end up with RBr plus water also. But how many steps we have here? 3. So that's the difference. So here, step 1 is what? Protonation. Step 2 is what? So step 2 and step 3 are really considered what? Together they are SN1, which is first carbocation and then substitution. Okay? Now, what did we say about secondary alcohol? So, what is the problem with secondary? So, they can what? Rearrange. So, you have 2 possibilities. Either the one with no rearrangement. So, if there's no rearrangement, what's the mechanism? How many steps? 2 steps. So ROH plus HBr. So you can have step 1 and step 2, which is protonation, and then followed by SN2. That is in cases no rearrangement. So if you have no rearrangement, you only have 2 steps, like a primary alcohol. Now, if it's secondary and you can rearrange, so for no rearrangement, you have 2 steps. But if there is a rearrangement, then you're going to have 3 steps. So here, step 1 is protonation. And then step 2 and 3 are the SN1. So that's what we studied last time. But we did something else. What was the last thing we did before we left? We said that when we work with HCl and primary in particular, it's very slow. So what do we do to make it work faster? Which is what? Lucas test. So the catalyst here is zinc chloride. So this works, all of these, they work very well if you have HBr and HI. If you have HCl, it's very slow, so what you do is Lucas, which is zinc. So I'm not going to rewrite the mechanism, but you're supposed to know the mechanism. And by the way, you can use it also for secondary and tertiary if you want. And that's what's going to happen next week in lab. We're going to do the Lucas test for primary, secondary, tertiary. I'm not saying that you can't use it, but it's best to use it if things go slow. You speed it up with some zinc chloride. So now what's the next step is chemists want to find ways, like, you know, if you dream of a molecule, they have to find ways to make it, despite all these restrictions. So if I want to put chlorine anyway, but I know that HCl is not reactive, you agree? It's not very strong, and I want to make it work fast. So how can I chlorinate or substitute with chlorine without using these methods? And also, how do I do it without rearrangement? If I have a secondary that can rearrange, and I don't want it to rearrange, is there another way of working with this? So here we're going to use Lewis acids, okay? So I want you to write it down so you understand when to use what. Is everybody clear? All these acids are what type of acids again? Bronsted acid. I want you to start to kind of always look at your substances as acids and bases, Lewis acid, Lewis base. So using Bronsted acid works best for what? HBr and HI, and it's slow for HCl. It's also slow for primary, and there is always a solution which is zinc chloride to make it fast. But what's the problem here is really for secondary you have rearrangement. So what's the best approach is to work with a Lewis acid instead of Bronsted acid. So that's what I want to do today. Show you the option. What happens if I use, instead of a Bronsted acid, a Lewis acid. Okay? So what they put in your book, we use PCl3 or PBr3. Now you see that PCl3, we have chlorine here, so you can chlorinate without having to use HCl. So how does it work? I'm going to take one example, just to be consistent with my example here. I'll just going to give you the general mechanism which applies to all of them, primary, secondary, and tertiary. Okay, so I'm going to put a COH. So when I put like this, it means it doesn't matter what type of alcohol, primary, secondary, but I need to show you that carbon, okay? So if we use PCl3, P, which is phosphorus, Cl3. So if I use PCl3, so it's PCl2 with this. And the reason I mentioned last time about compounds, if you look at phosphorus here, and this is going to happen again with other elements, it's period 3. So the configuration for phosphorus is neo, and then what? 3s2, 3p, 3. So it means each orbital has one electron, and that's the reason it makes PCl3, you understand? But it's period 3, so what comes next after 3p? What's the orbital after 3p? 3d. And that 3d is empty. So what is a Lewis acid? It's always an atom with an empty orbital. So phosphorus is a Lewis acid because it has the 3d orbitals completely empty. So how do we represent it? We just put a box like this. So that's what makes it a Lewis acid. So everything from period 3 and higher, you have phosphorus, you have sulfur, you have silicon, and you have everything at the bottom. Chlorine also can be a Lewis acid, bromine can be a Lewis acid, they have empty d orbital. Okay? So what happened with this d orbital? What happened is this lone pair will dock into this orbital. So it becomes what we call a covalent. It's a coordinate covalent bond. What is a coordinate covalent bond? Normally a covalent bond, each atom gives one electron. You agree or not? You learned this. When the one atom gives two and the other one gets them both, it's called coordinate. Okay? So it happens between acids and bases. But at the end, you end up with covalent bonds. So you can make a bond by adding 2 electrons at once. So when this docks, this leaves. Okay? So you have a Cl leaving, and you end up with OH, I put the H here, and PCl2. So the first step, when we use the Bronsted acid, the first step was what? Here. Protonation, which means the acid, the H plus, attached to the oxygen. In here, what attached to the oxygen? It is the Lewis acid. So it's always the acid that attaches to the oxygen. So both are the same, except that with the Bronsted, it's H plus that attaches. In here, it's the Lewis acid that attaches. I'm trying to give you this to make you remember, like how are they similar and how are they different. So step 1, the Lewis acid is attached to the oxygen. But you notice something here, you have to release the chlorine. In the previous case, we didn't have chloride leaving, okay? Then, the second step here, this is positive. So here we bring pyridine. Now you will see pyridine coming a lot. So pyridine is a very mild base. So this is called pyridine. I'm going to use a different marker for that. And in these reactions, you'll see it written on the top of the arrow, meaning it's a catalyst. It's just there to help clean up the act. You understand what I mean? It's like, it will clean up a little bit. Whatever you don't need there, pyridine will take it. So what do you think is going to take? Where's the pyridine? The base will take what? What do bases do in regular reactions? Take the hydrogen. So here, that hydrogen is in the way. You agree? Because oxygen is not stable. So the pyridine will take this H, and then the oxygen will take its own care. And then this is pyridinium ion. So step 1, the Lewis acid attaches to the oxygen. Step 2, pyridine removes the H plus. And then what else we have here? Because we still have a Cl minus. So in this scenario, the Cl minus now can come here. Why? Because this is a good leaving group. It's bulky, it's big. So the Cl minus here will come, attach to the carbon, and then the phosphorus will take the oxygen. So step 3 is the Cl minus attacks, and you end up with Cl plus now that's negative, and pyridinium ion is positive, so what's going to happen between them? They neutralize, and then you regenerate your pyridine. That's how you know it's a catalyst. When they write pyridine on the arrow, it means it's there. You need to recuperate it at the end. So I have H and plus. So last step is the oxygen takes the H, and you end up with POH, CO2. And it's good for phosphorus, it has 3 bonds, plus the pyridine. So now that pyridine will go again and react with the next bond. So what does does this mean? It means whenever you work with alcohol, if you want them to react, you have to react them with an acid. The mechanism with the Bronsted acid is very different with the mechanism with the Lewis acid. So, one thing you should keep in mind that if you use a Lewis acid, you have to have purity. Even if it's not written there, you will see it in some questions in the problems. If you use a Lewis acid, you have to have purity, even if it's not written. You have to know that you have to have a base to deprotonate the alcohol. Okay? No matter what, you have to have purity. Yes?
Professor, I'm just confused. Where did the carbon chlorine go into that?
The chlorine was here. Now it's on the carbon.
And then it's still there at the end, right?
Yeah,
Okay.
yeah. But I'm just showing this part.
Yeah.
I'm just showing this part here. We'll do this. Okay? I have to just show the whole final step. So the final step doesn't involve the RCF. Any questions about this? So here we use the Lewis acid that is PCl3. We could have exactly the same result with what? PBr3. So exactly the same. So using PCl3 or PBr3 will give you the exactly same result, except that in here you end up with bromine instead of chlorine. Yes?
Can we also use SOCl2?
We're gonna get there. Okay? So is everybody understanding this Lewis acid situation? So it works with PCl3, PBr3, and it works with all the alcohols. But this works perfectly for secondary because there's no rearrangement, there's no carbocation formation. Now remember, carbocation only requires strong Bronsted acids. You can never produce a carbocation without a Bronsted acid. So all the mechanism we're going to see, if you use a Bronsted acid, you form a carbocation. If you don't use a Bronsted acid, you can never form a carbocation. So remember that in synthesis. If you want something without rearrangement, never use a Bronsted acid. Use a Lewis acid. Okay, next is SO. We have another option of Lewis acids. So here we use PCl3, and I said it's the same with PBr3, so I don't have to put it there. But you have another option which is SOCl2. Okay, so if we use SOCl2, also look at this. Phosphorus and sulfur are both on period 3. So just like phosphorus has empty d orbital, sulfur also has empty d orbital. That's the reason in 201 or 200, when you do the expansion, like some atoms go beyond the octet, because they have that empty d orbital. So if I put SOCl2, so it's S, I'm going to be consistent with the colors, the blue will be from the mechanism, so you don't get mixed up. So I have sulfur has an empty orbital, okay? It has a Cl here, it has an O, and it has another Cl. So this is SOCl2. I'm sorry. Yeah, SOCl2. Yeah. Okay, so the first step, just like the previous scenario, the first step is always the acid attaches to the oxygen. But then in the same process, the chlorine needs to get out. So every time you use a Lewis acid, one docks, one leaves. Bronsted acid, you don't have one leaving. You just have the hydrogen docks. That's it. So we end up with and again, what did I say? Every time we use a Lewis acid, what do we need? Pyridine. No exception. So these are the things that you will see repeating. Lewis acid, no catalyst, no pyridine. I'm sorry, bronsted acid, no catalyst. Lewis acid, you always use pyridine. So pyridine will come here, and it will grab that proton, and then the oxygen takes its proton. It's the lone pair, sorry. So what's the next step if we kind of compare it to the previous scenario? What's next? The chlorine has to attack. So I have this, and then I have a Cl minus. You see, you have the pyridinium ion and the Cl minus. So now the Cl minus can attack. Why? Because this is a very good leaving group. But this is what's different between this and the previous scenario. I want you to follow me here, okay? So the chlorine will come on the oxygen, but here's what happened. This makes a double bond, and the other chlorine takes off. So why? Let me show you what happened here. You end up with Cl. So that's that first chlorine is back now on the molecule. And then what do we have there? We have SO2 gas. So what does the SO2 gas do? It drives the reaction to completion. You understand that if the product escapes from your mixture, it makes the reaction go to completion, the Chateaubriand principle. So this is a much better choice because the minute you produce a gas, the gas will completely make the reaction give you very high percent yield. And what comes with this, we're still going to end up with Cl minus and this. Okay? So you end up with Cl minus, because that's the other Cl minus, and then the pyridinium ion. And these two will give you HCl plus pyridinium. Okay? So you start to now see that we have different options, and they're going to appear again and again and again. Lewis versus Bronsted, Lewis versus Bronsted. How are they similar? How are they different?
So going back to your point about not rearranging, is it because that leading group is so good that the chlorine will always want to go?
Yeah, you can't have a carbocation. To have a carbocation, you have to have a Bronsted acid. That's always the case. So here, there's no Bronsted acid. As long as you don't have an HBr, HCl, and H2SO4, you can never have a carbocation. Okay? Remember, carbocations can only form in the presence of Bronsted acid. The minute you put Lewis acid, that docks in there, it's not going to do it. So that's what makes it different. no H plus there, so the carbocation won't. So what are the advantages and disadvantages of using Lewis versus Bronsted? I'll tell you one thing. Why do we have to give you all of this? One thing is these are cheap, okay? HBr, HCl, easy to use. So if I want to do a quick and easy transfer from an alcohol to an alkyl halide, I can use these. But you will do it in lab, actually. I put a lab there where you substitute an alcohol into an alkyl halide, and you're gonna see the percent yield. The percent yield is not that big. The only way you can have a high percent yield is using SOCl2. So chemists need to find different methods. If I want to have a quick and easy and cheap, I'll do this. If I want higher percent yield for something more sophisticated and get really pure product, use SOCl2. Now, what is the problem with the sulfur? If you work with sulfur in any lab, everybody will hate you because it smells like rotten eggs. So what do they do in research? All the labs, and I'm not kidding you here, all the labs that use sulfur, they put them in the top floor so that the exhaust will move the fumes out and nothing will come from the third floor to the fourth if there's any problem with the exhaust. So that's the problem with these compounds. They're smelly, and if you don't have a good ventilation, you can have bad, consequences. But it's also good for you to understand why we have many options. So you know when you do synthesis, which one should I use? If I have a secondary carbocation that can rearrange, I'm not going to use Bronsted. I'm going to go straight to Lewis acids. Okay? Any questions? Is everybody clear with this? Yes.
Would the chlorine ion that you form in the first step ever interact with the hydrogen instead of the pyridine?
Which one?
The
This
first
one?
The first chlorine.
No, because it's not strong enough